right, guys, it is 4 o'clock. I think I'm going to go ahead and get started. Welcome to Thursday. I hope that you guys are doing well. And I want to make a few announcements before we get started here. First of all, a really big thank you to all of you. I think every single person watched my video. And I know it was kind of long. There's a lot there to it. We are going to review it, of course, today. The idea is now you at least have a little preview of it, and we can do even more examples and practice the ideas from that group work. But I'm going to do an extensive recap of the video in just a few minutes. So thank you so much for doing that. Because I was giving I had these exams actually already graded last night. And I'm going to give you back your exam in a little bit. The reason I didn't get the grades up very quickly was I was just waiting to try to give everybody the 4 points for the video. And there were a few people that just got it in like an hour ago or something. So I was just getting that finished up. So I'll pass back the exams in just a little while. Overall, I was really happy with the results. I have to tell you, I was quite pleased with it. The only thing I didn't really care for, I'll just get the bad part out of the way before I even get into it, is that for the remainder of the semester, when we have an exam in here, I have another class right after this one, and they come in here and take the same test. So I don't like all the hallway conversations. So on your second midterm, on your third midterm, just take off once you're done. Don't mingle in the hall. The other class doesn't need any extra help. I think they probably had a slightly higher average. And both classes are very good, but you guys are being curved against them as well. So if you're not helping your own grade, I'll put it to you that way. Anyhow, other than that, which annoyed me a little bit, the results really was quite good overall, I would say. I'm not saying everybody's, had a great day with flying colors with this exam, but there was a lot of good scores. I didn't actually calculate the average and the median yet because I literally was adding the 4 points and it was changing all the data a little bit. So I can't tell you exactly what it was, but I do know there were a lot of people well above 80%, above 90%. In my other section, I think there was actually 3 people above 100% by the time I added those bonus points. So it was quite good. If you personally didn't feel so good about it or didn't do so well, you're like wondering, well, what are you supposed to do next to try to improve? Of course, I always want to remind everybody that we're all on the same team. I want everybody to do well. So if you don't feel good, basically it means I don't feel good either. Like I kind of feel the way you feel about it. So, if we need to make some changes, if you're in a situation where maybe you want to come talk to me personally, I'll have a private conversation with anybody about how they're doing. That's certainly fine. Of course, I have my office hours. I always encourage people to come. The other thing I wanted to mention is there is an SI session for this class that unfortunately it runs right now, like right while we're in class. And it's being run by my best 250B student from last semester. She is super, super good. She got over 100% on all of my midterms. And so she knows this stuff really well. And not only that, she knows how I teach it. She knows kind of how the course is going to progress. If you think you might benefit from going to that SI class where you'll get extra practice, she has told me there's a few spaces that she has available. And I would be, if it works for your schedule, we don't need to change anything on your official roster or anything, but you, of course, are welcome to attend my 6 o'clock class. So if you wanted to go to the 4 o'clock workshop and then attend my 6 o'clock class, that would be fine. Actually, that would be fine pretty much anytime. If your car breaks down in the afternoon, you can't get here by 4 o'clock, but you can come by 6. I would rather have you do that than just staying home. Because at this point, you can see there's a few seats available. There were a couple people who didn't take the exam. I'm pretty sure that those folks may be not going to be coming back. So I have some flexibility with that. I've told my other class they can come attend to this one a little bit too. So kind of back and forth. So if you think that might be helpful for you to go to the SI session, you certainly can do that. But other than that, absolutely feel free to come talk to me. When you get your exam back, I'm going to really encourage you to go through it and read my comments. I try to make some good comments about anything that maybe could help you with your understanding. And I've posted the solutions to the midterm in our Canvas homepage as well. Sit down with the solutions and with your exam, and let's make sure that you can look at that and say, yeah, I could do everything on this exam, right? And if there's anything missing, come talk to me about it. Last semester, I had some students who, for whatever reason, even by week 12, I'm noticing they still can't do the EROs, right? It's really not going to be good, right? We're going to be needing those EROs all the way to the end of the semester. So if that's something that's still a sticking point for you, don't be shy about that. I'm not going to judge anybody. I know this is all hard material. I totally get it. It was hard for me, right, when I learned it in the first place. So if you just need some extra practice, or just want to talk to me about even something that you think is basic, I hope that you won't hesitate to bring it up to my attention so I can try to do something to help you with that. Okay, but anyway, overall, I was really pretty happy for the most part with how things went on the exam. So yeah, that was good to see. I'll try to send out an email later on with sort of more of what the results actually were, because like I said, I was getting dizzy just collecting the video assignments and putting the points in there for that and all that. I just didn't quite have the final numbers to like do a good calculation. So I'll work on that. But anyway, that's kind of where we're at. Also, don't forget, I have a grading scale that's a little more generous than your usual 90, 80, 70 for A's, B's, and C's. I have more like a 12.5 point scale. So an A minus actually goes all the way down to 87.5, and a B minus goes all the way down to 75. The scale is in my syllabus if you want to review it, so you kind of know where you stand right now. So anyway, I'll give back the exams later. I don't like to do it right now because I've tried that before. You know what happens if I pass back the exam right now? Everybody just reads their exam for the next 15 minutes and I'm trying to do new material. So I don't like that to happen. So I'm going to give it to you towards the end of the class. Okay, but you'll get those back soon enough. Yeah, right. And also, I guess just to sober us up a little bit, I do want to say that many students in the past who've taken this class will probably agree with this, which is that to some extent, those first 3 chapters is kind of the most straightforward. What I mean by that is it's a lot of computations. It feels a little like calculus, solve the Bernoulli differential equation, do the determinant calculation, EROs, right? This is very computational stuff. It's not quite so, abstract out there. And so some people, I'm not saying this is true for everybody, but some people will tell you that, yeah, when I get to the chapter 4, everything kind of goes sideways on me a little bit. Whereas chapter 3 was 3 sections long. It was only 2 lectures. The longest chapter in the book is chapter 4. There are 10 sections. This is a big chapter that we're heading into right now. And so let's celebrate a little bit about the exam, if that's your situation, if you feel good how you did. But don't celebrate for too long because we've got a long way to go still. So I just want to keep everybody working hard. I'm going to keep working hard, of course. You guys know that too. So anyway, the first step to kind of getting through chapter 4, what I realize is that having us watch that video really gives us a nice boost into it rather than just having to start totally from scratch. So I've got some notes here that I'd like to start reviewing with you briefly. The idea, as I talked about in my video, is we're going to learn about something called a vector space. This is an abstract framework. It is an apparatus which is consisting of vectors. Now, these are not vectors in the traditional physics sense that you might have seen, or even in a calculus sense. These are not vectors in sort of a classical technical sense. These are abstract vectors. These vectors could be pieces of fruit. These vectors could be office furniture. These vectors could be the colors of the rainbow. They could be weird objects, but the vector space has objects in it. And those objects have to be manipulated with some kind of an algebra structure. And so there's 2 operations that we have in a vector space, and they are, you saw them in my video, addition and scalar multiplication, right? Those are the two operations. So I'm going to allow us to take strawberry plus banana and get another answer out of that, right? Or green plus purple. There'll be an answer for what that equals, right? So we can take these vectors and add them together, or we can take a scalar multiple of a vector. So we can take pi times desk, right? And we have to get some other office furniture out of that. And so it's kind of weird because the vectors can be something you're not really expecting, right? However, there are some standard vector spaces. There are some vector spaces that are going to come up more often than any others. Oh, and before I go through this list, I wanted to point out in Canvas, I've got my screen up over here. If you go to the files section over here on the left side, I'm going to click on that real quick. There is a folder called special handouts. And I'm going to click that one open and go way to the bottom. There is a document called Vector Space Axioms. I think I actually attached this to my email, and some of you might have already seen this, but just to get it up here one more time. This would take like 20 minutes just to write down this whole handout. And I realized there's not really a good point to doing that in this class. So what it is it's really the definition of a vector space. It takes like an entire page to write down the definition. So I've already talked about the fact that you have to have vectors, right? The vectors are the objects in the vector space. And you have the two operations of addition and scalar multiplication, right? But then on top of that, there's all these rules. There's 10 of them. 10 rules that a vector space has to satisfy in order for it to be a legitimate vector space. And it turns out the first two rules, I guess we can see them here already. The first two rules are the most important ones. Center a little better here. The first two rules, the closure under addition and the closure under scalar multiplication, those are the most important ones. So if I take strawberry plus banana, the answer has to be in that same universe. So strawberry plus banana cannot be equal to green, right? Because green is not a fruit. Strawberry plus banana might equal cherry. That would be okay, right? So it has to be an output that's in the same universe that you started with. Same thing with the scalar multiplication. If I start with one vector and I multiply it by a scalar, which I usually call k, the result must still be another vector in that same universe, right? In that same vector space. And these turns out, A1 and A2, these turn out to be the most important of the axioms. Okay, the rest of these axioms, A3, A4, A5, and all these rest of these axioms are just standard algebra properties that you are probably already kind of expecting. Like you're not surprised that when you add two vectors, it shouldn't matter what order you do it in. Or when you add three vectors, it doesn't matter how you put the parentheses, right? The commutative law, the associative law, distributive laws. Like this A7 is really silly. 1 times V has to equal V. Okay, so that's definitely going to be true for any examples that we look at. Now, if you're really craving, some interesting examples where some of these other axioms are a little bit weird, then all you've got to do, and I'm sure you're already in the process of the paperwork of adding math to one of your majors, that by the time you're a math major, you will have to take Math 307, which is the upper division version of linear algebra. It's even more theoretical than this class is, actually quite a bit more theoretical. It's for math majors. And in a class like that, they are going to give you some weird vector spaces, like with fruits or colors or whatever, right? And they're going to make operations that are kind of funky, that don't behave in the way you would expect them to. So where 3 plus 5, 3 quote plus 5 is equal to 15 instead of 8. We'll do some weird things like that, and you can create vector spaces where that's actually possible to have weird operations on the vectors. So you'll see examples of that in some of those other classes. They are in this book as well. So if you want to look at the exercises in here, I think it's section 4.2, there are some nice examples of sort of weird constructions of vector spaces. Back in the day, I used to try to actually assign a few of those and kind of have people play with that a little bit. I realize it's probably not the most important thing for 250B, and it's really, I don't know, it's a big lift for us to try to do all of that. So I'm going to stick with the standard script here, guys. Okay. If you're looking for more interesting examples, you can either look in the exercises of the book here, or you can take Math 307, which is a great class. I've taught it many times. And it will give you a more abstract view of linear algebra. But what are these standard quote unquote universes that we are mainly going to see in this class? Well, I've got them all laid out here. And these were all the ones that you saw in the video that you watched. Rn, right? Now, of course, everybody's very familiar with R2 and with R3. These are just the XY plane and the XYZ 3 space. But here, n can be a much larger number. N could be 4 or 5 or 6. N could be big enough that we actually can't draw the pictures anymore. But that's okay, because this isn't about drawing pictures. This is not about this is not called linear geometry. This is called linear algebra. It's all done with algebra. So we don't need to be able to see pictures to do this stuff. But Rn is just a list of n slots. And anybody who's worked with a spreadsheet knows that sometimes you'll have more than 3 slots. So yeah, you have to be able to deal with values of n that are bigger, where you don't have pictures that you can draw with your vectors. Okay, what else do we have? M by n matrices, right? Those also form a vector space under the operations of usual addition and scalar multiplication, which we went over, right, in chapter 2. We've already talked about matrices a lot. In fact, they could be n by n matrices. And that would also work. We have a slightly different notation here, right? By the way, I should point out, notice that the matrices, this is worth reflecting on for a moment. They don't have to be square matrices. That's okay, because after all, the only thing we're doing is adding them together and doing scalar multiplication. If a vector space also required us to do regular multiplication of our objects, we would have to take the second one off our list. Because can you take a 3 by 4 matrix and multiply it by a 3 by 4 matrix? Would that work? Sure would. It sure wouldn't, right? We all know that, to multiply 2 matrices, these numbers in the middle have to match. Oh, so that means that we can't do matrix multiplication in this universe. Oh, but that's okay, because a vector space isn't going to require matrix multiplication. It only requires addition and scalar multiplication. Those are the 2 operations. Are you with me? I know it seems a little weird. We just learned how to multiply matrices. Do the dot products of the rows of the first matrix with the columns of the second matrix. And now all of a sudden, 2 chapters later, Dr. Annan is stripping that away. You think, no, we're not going to do that anymore. We're only going to do addition and scalar multiplication. That's just the way it is. Okay, for vector spaces, that's the rules. Okay, so anyhow, as long as we strip away the regular multiplication and stick with addition and scalar multiplication, the matrices don't have to be square sized. Okay, perfect. So we've got matrices as good examples. I talked in the video about polynomials. This is a nice one. Polynomials of degree. The degree is kind of important here. Of degree less than or equal to n. So you'll see that if you look at the terms here, of kind of what one of these vectors looks like, each one of these polynomials is a vector. And if you look at the terms, you can kind of see that they don't go past x to the n, right? These a0 and a1 and a2, those are just numbers in your polynomial. And some of those numbers, by the way, could also be 0. And that's why this says at most n here. Polynomials of degree at most n. That's because a sub n could be 0. In which case your polynomial actually would have a lower degree. If there was no a to the n here, we wouldn't have an x to the n here. Okay, so you have to allow these lower degree terms as well. So that's P sub n of r. By the way, you're going to be seeing these notations all the time, all the time. And the last one is sort of the one I think of as calculus functions. These are just functions from some interval spitting out real numbers. Okay, so when you think about what this C of AB is, just think about calculus functions. Sine of x, e to the x, whatever. You can add functions together like that, and you can take a function and multiply it through by a constant. That's perfectly legal. This one, the calculus functions one, will become much more important when we go back to the differential equations later in the semester. After all, the solution to a differential equation would be a function. We would write it as, y equals something. So it would be a function. And so this universe down here will be really important in the last month of the semester when we're going back and tying in the differential equations again. But all of these are great vector spaces to work with and that we can learn from. Are there any questions about kind of this overview of these standard, what I call universes that we'll be working with? Yeah, Antonio?
I have a question on the calculus function in the video.
Okay, yeah.
So it was one where we had a over b, where b is not equal to 0, and we were checking it against the scalar multiplication.
So that's not calculus functions, right? That's fractions, right? This is the vector space of rational numbers, I believe I called it. Yeah, okay. So that's what we're talking about. So the scalar multiplication.
You said it fails under the condition that we multiply by pi.
Yeah,
We're just wondering if
I can, and it's also in the homework that you're going to be doing. I forgot to mention the next homework assignment will be due on Tuesday. So I have the whole weekend to work on it, but it is fairly long. And it's got obviously all this material in it. So you'll want to start it a little bit on the early side. I will take some questions on it on Tuesday, but since Antonio has brought it up right now, this is as good a time as any, right? So if we take our vector space to be Q, which is just a notation for the set of rational numbers. This is just any numbers that can be written as a fraction of two whole numbers. So this is just the set of A over B, where A and B are integers, and B should not be 0, of course. We do not want to divide by 0 here. So the question they ask you is, well, does that form, is this closed under addition and scalar multiplication? And it is closed under addition, and you guys can imagine that. I did it in the video, right? If you take A over B and you add C over D, you can make a common denominator and write it as another fraction in the same form again, right? But with scalar multiplication, the question is, if I multiply by a scalar onto a fraction, will I get something else that looks like the same form again? Right? Is it still a fraction? Actually, let me be more careful. Is it a fraction of two whole numbers? That's actually the issue, right? So if I let k equal pi, for example, this is what I did in the video, that's a perfectly good scalar. So I'm using k, you see it here? The scalar, I like to call it k most of the time. And so let's just take an example here. K is equal to pi. Let's pick a fraction that's really easy. I don't know, 2/3 would be a nice one, right? So you take something that's in Q. This is like taking strawberry and scalar multiplying it by something. Do we get another piece of fruit again? Do we get another output that's in the same universe? Well, the problem is some people will look at this and say, oh yeah, that's still a fraction. But the problem is it's not a fraction of two integers. These are whole numbers. This Z notation means 1, 2, 3, 4, right? This pi is, what is it, 3.1415, and it's got a big long decimal expansion. This is actually not in Q anymore. Okay, so you'll be writing something like this down on your homework problem. So closure, the way I would write this is closure under scalar multiplication fails. And if some property fails, I can give just one specific example to show that it's going to fail. I don't have to take any general notation. I can make it really super specific, which is what I just did right here. You see what I mean? Does that help? Yeah, okay. Does this make sense to everyone? This is not a vector space. Because this axiom, which is actually, by the way, this is the same thing as A2 in the list here, it fails. Closure under scalar multiplication fails. And as soon as one of these 10 rules fails, if even one of them fails, it is basically game over. Right? At that point, I don't care if the rest of the axioms are true or not. If there's even one axiom that fails, we can stop. And we just need one example to show that something would fail. Yeah.
Can you elaborate again on this 2 pi?
Uh-huh.
You did not on the cube because pi is like what 3.14 something like it's still a real number.
It's real, but it's not an integer. The numerator and denominator have to be integers here.
Oh, okay.
Pi is not an integer. We're not allowing approximations. This is an infinite decimal. What is it? 3.14 or 15. Pi Day is coming up, by the way, March 14th. 314. So anyway, it's got an infinite decimal expansion. And so that goes on forever. And so that's why it's not in the right form here. Yeah. Yeah, pi is an irrational number. And your scalars, your choices for what k is, has to be open to any real number. And so I've chosen one here. Did I have to choose pi? No. Did I have to choose 2/3? No. I could pick any scalar, any vector, and if I multiply them together and don't get another fraction of 2 whole numbers, it's not closed under scalar multiplication. Right? So we've got 35 people here. We could have 35 different little box calculations like this with different choices of k and a over b, and we could get lots of examples of that. But we only need one to show that it fails. When something fails, I only need one example to show that it fails. If I say that all Saturdays are sunny, right? All that you have to do to prove that I am wrong to say that all Saturdays are sunny is just wait until there's a Saturday that's not sunny and say, see, here's my example, my one example that shows that your statement is false. That's the kind of the way you want to approach it. Okay. Yeah, but these different universes here are not normally what we're mostly going to be interested in. We're actually usually going to be interested in some set that is inside of this massive universe that we have in the vector space that's one of these in the background. What's actually usually going to be more important to us, guys, is some subspace that is inside of one of these universes already. Let's say that I ask you, well, let's just, again, I'm just gonna, you don't need to take a lot of notes here yet. I'm just kind of warming up for this chapter a little bit. Let's just take a differential equation here. Something like that, okay? There's a differential equation. What I might really want to do is solve this for y. In other words, I want to find which calculus functions satisfy this. This is a second order, linear, homogeneous differential equation, right? We're going to learn how to solve these later on in the semester. But the solutions to this differential equation consist of calculus functions. But not all calculus functions are going to solve this differential equation. It's going to be some of them. It's not going to be the entire vector space of the continuous functions from an interval to R. It is going to be some of them, right? It is going to be some functions that happen to solve this differential equation. And that's, if this is your problem, if this is your real world differential equation, it's the solutions to this that you actually care about, not the big universe so much. So we're actually going to spend more time talking about these important subspaces that are inside of one of my big V's here. right? That's actually what we're usually gonna look at. So a subspace is inside of V. And it still has to have closure under addition and scalar multiplication. But you might wonder, well, what about all of the other 8 axioms? There's 10 of them over here. Technically, a subspace is just a vector space inside of V. But you see, V is already good with commutativity, associativity, unit properties, et cetera, right? V has already got all of those axioms. Well, guess what? S, which is inside of V, is going to inherit those good properties from V, right? If I make the statement that everybody in California has a valid driver's license, right? Probably not true, but let's just say it is. Everybody in California has a valid driver's license. Then in particular, that would mean that everybody in Orange County would have a valid driver's license, right? So anything that's true about the big universe already, if we already know that our big V has all of those 10 rules, then S will too, except with the possible issues of these 2 closures, which are A1 and A2. This is A1 and this is A2. You can call them either way you want. That's why I spent so much time in that video focusing on A1 and A2, right? Because those are the axioms that if you show those 2 axioms, the rest of them get inherited by S, and that would make S into a vector space in its own right within V. I drew this picture, right? You have S here, and V is just the big vector space outside of that. So S already inherits most of the algebra rules from V. The only issue is, well, we got to make sure that is still closed. That when we add 2 things from S, we get something back in S again. Or if we take one vector in S and multiply it by a scalar, the result is back in S again. That's really where the heart of the work comes into it. So I had a couple of examples in the video. Maybe inside of the big universe of n by n matrices, that's my big V, right? But maybe I only care, for my purposes, I only care about the symmetric ones. So the n by n symmetric matrices, and in my video, you guys have it in your notes, you showed, or I showed that this symmetric matrix set is closed under addition and scalar multiplication. We actually wrote it all out in the notes. And so that means it is a subspace. It is a vector space in its own right. And maybe those are the vectors that I actually need to work with for my real problem that I'm working on. Okay. Another example, and this one's a big deal. This came up right at the end of that video. Null spaces. Actually, null spaces, I could have explained those in chapter 2 if I had wanted to. They are really just solutions to a linear system of equations. So if you have a system of equations where all of the right-hand side of all of the equations are 0, if they're all just equal to 0, then the solutions to that, well, they form a subspace of Rn. Notice the matrix is M by n, but the null space is actually inside of Rn. That's because the solutions, these x's, have n slots in them, right? And again, in my video, I showed that a null space is always closed under addition and closed under scalar multiplication. You can change this matrix 500 times and have 500 different linear systems, and it would be crazy to have to stop each of those 500 times and recheck that it would be a subspace that is closed under addition and scalar multiplication. But luckily, we don't have to do that because you guys are my witnesses. I proved it in the video. I hope I did it right. Okay, I hope that you liked my video. I mean that you liked my video.
Yeah, I did.
Good, because after all, if you watched my video and you saw me prove that a null space is a subspace, guess what? You never have to check it again. It is from this day forward true. You guys will never have to check it again. There's only one person in this room who will ever have to check it again, and that is me 6 months from now when the next students come in and I have to explain this all over again from scratch. Okay, but anyway, you guys have seen it and you know it, and so a null space is always a subspace. Don't even have to say another breath. Don't even have to take another breath, you just say it. If you see a problem where you're like, oh, the vectors that he's talking about, they are just a null space of a matrix. You just have to quote that fact, write it down. Okay, so anyway, that'll save you a little bit of time and effort. Well, I'd like to do a little bit more examples of this. I've got a couple of them, obviously, that you saw in the video, but I'd like to do a few more. First of all, question. Yeah.
Will that null space, will that also be subspace, just inside R10?
Yes, that would also work. I'm not gonna get into left and right null spaces here, but yeah, absolutely, we could do something on the other side as well. Yeah, good point. Okay, let's do a few more examples. I'm gonna go, I'll call these warm-ups here. And then after we warm up with this, I'm gonna have you guys do some group work and practice this a little bit on your own. So here's the warm-ups, guys. Which sets below form a subspace of V? Put this up now. I think I'll go ahead and mute this other screen of axioms for the moment. We don't really need to work on it too much. Okay, so let's do 2 or 3 of these right now. So the first one, I'm going to take the vector space to be P3 of R. This is number 1. Let's take P3 of R. So are we all comfortable with what that is? Those are just polynomials that have a constant term. So A0 plus A1x plus A2x squared plus A3x cubed. It's basically what it is. And what is S? S is going to be, so when I say which sets below, those are which sets S below. So S is going to be the set of P of X, which is an element of V, such that P of X is equal to AX cubed plus CX. Let's take this example. So I'm looking for whether or not that is a subspace. Now let's just see how you guys are coming along with my video, because there was one thing that I mentioned in my video that I have not mentioned so far today. The real issue is really asking if it's saying, does it form a subspace or not? I'm really just asking, is it closed under addition and scalar multiplication? These two things, right? But there is another thing in my video with the examples I did that I sort of did first. Does anybody remember what that was?
Zero vector.
The zero vector check. Good call. It's actually A5 on the list of axioms. Existence of a zero vector. Every vector space has to have a zero vector in it. That's a vector that when you add it to anything else, it just leaves it alone. So if strawberry plus banana is equal to banana, and strawberry plus peach is equal to peach, and strawberry plus grape is equal to grape, strawberry is your zero vector. You add it to anything else, it just leaves it the same, right? So there has to be a vector like that. And of course, in P3 of R, there is a zero vector because it is already, we already know it is a vector space. By the way, each one of these, you had to check, all 10 rules had to be checked. Okay, we're not gonna do that. You guys will all be asleep by then, and so will I. It's not very exciting. So we're taking it kind of for granted that you could check all these axioms. But so there is a zero vector for each one of these universes. But the question right here is, and I like to do this zero vector check because if it fails, if this test fails, we can say, no, it's not a subspace and move right along. Okay, so we know that there is a zero vector. The question is, does it belong to S? So is there a polynomial that's in this universe? I mean, if you think about what the zero vector is here, I mean, it really is just 0. Now, when I write 0 here, guys, I do not mean the number 0. We're not working in a universe of numbers. We are working in a universe of polynomials. When I write 0 here, I am thinking of it as, something in the P3 of R. But you can see, for example, that I can put the A and the C, those are just the scalars. I can put the A and the C both to be equal to 0, and I can say, yeah, that is in S. That is in S. Anything that has this, so this just means belongs to. Kind of went over this in the chapter 2, I think. So belongs to S, right? Because anything that looks like that form belongs to S. Something x cubed plus something x. Anything of that form is a vector in S. And the 0 vector is in that form because I can write it as 0x cubed plus 0x.
Let's say your x, they have a addition of, let's say, a constant of 4.
I'm gonna do that next.
Oh, okay.
Yeah, I'm gonna do that next. Yeah, you're thinking ahead. We can mess this up very easily. Yeah, but for right now, this is in S. So it passes. I put a little check mark, meaning that it passes. So that means that we have to keep going, right? We're not ready to move on. So now I've got to check the closure under addition. I'm gonna try to check the closure under addition here. And that means, how does the closure under addition work? It means I start with 2 vectors in S and I'm going to add them together and see what happens. So let's do that. Let's let ax cubed plus cx, comma, and then I need some different letters of the alphabet. My second vector needs to be different notation. Let's say rx cubed plus sx. Let's let both of those be in S. Notice I put a comma between the two. So I have one vector in S and I have another vector in S. And what I would like to do right now is add them together. So then I'm literally going to add them together. Ax cubed plus cx added to rx cubed plus sx. I just want to add them. And the question is this still in S? Now, anything that's in S has to have this form right here, meaning some cubed term and some x term. Nothing else, just that. Would you say that this is in that form? We might have to do a quick little rewrite of it. I'm going to go ahead and do that. Is it okay if I regroup the terms a little bit? How about we put the x cubed terms together, right? So that would be the quantity a plus r times x cubed, and we're adding that to, let's say, c plus s, that quantity also times x. By rewriting it like this, and I would want to see that, right? I wouldn't want you to just overlook that. That's a key step to re-express it, to reformat it so it has this form. And it does, so we're going to put a check right on top of that one. Exactly. So that is closed under addition. Okay, everybody with me? Okay, let's go to this other board and check the scalar multiplication. Remember, if at any moment one of these axioms fails, we get to stop, right? We don't have to go on. But this passed, the 0 vector check passed, the closure under addition passed. Let's try the scalar multiplication. Okay, so with scalar multiplication, let k be an element of the real numbers. We have to grab a real number, and I'm going to call it k. And then consider, we're really just going to look at the same polynomial again, ax cubed plus cx, which is in S. Okay, this time we only need one vector. So for the addition, we had to make 2 vectors that we could add together. Here, we only need to take one vector and one scalar, and I'm just going to do the scalar multiplication. So then k times the quantity ax cubed plus cx is equal to, now, what we're trying to do is see, is it in the same form that the vectors in S have to have? Well, I can go ahead and just multiply the K into the expression. So Ka x cubed plus Kc x. And does that have the right form? The actual letters that are in front of the x cubed and the x, those don't matter, right? They can be any real numbers. So this Ka is fine, and this Kc is fine. It's got an x cubed term, it's got an x term. I would argue that is in the right form. It is in S, and therefore, thus, S is a subspace of V. Okay, we have to write that all out. There's not really any shortcut here. We are going to learn some shortcuts. I mean, you already have learned one if we have a null space. But null spaces, as you can see, they involve Rn, they involve matrices. It's not a polynomial context. So this sort of fast idea here of using a null space is great, but it does not apply if my universe is polynomials. So far at least, when somebody gives me a polynomial example, I can't use the null space thing. I have to go back to this sort of starting point. Just check the two axioms: addition, closure under addition, and closure under scalar multiplication. Okay, let's do a second example. I'm gonna just mix this up just a slight little bit. Let's take the same vector space V, P3 of R, V equals P3 of R, and let's take S to be the set of P of X, element of V. P of X is an element of V, such that, remember the two colons, you're going to see those a lot. It just means such that. But this time, what we're going to say is P of X equals AX cubed plus 5X. So instead of AX cubed plus CX, now I've actually got a specific number there. AX cubed plus 5X. And the question is, does that change anything about our answer? So the first one was a yes up here. Sorry, number one was yes. It is a subspace of V. But now what about this one? Does anybody see any differences here? Awesome. Yeah, I've changed the C to a 5. Now, let's just take it from the top. What about the zero vector check? Let's come over here to zero vector check. You have to know, does that pass or not? Well, guys, the zero vector is still the same zero vector that it was in example 1, because you're still in the same universe, P3 of R. So your zero vector would be, 0. So the zero vector is just 0x cubed plus 0x. It's the same zero vector. That hasn't changed. The question I have for you is it in S? Does that have the right form for the vectors that are in S this time? No. Anybody who's going to claim to live in S has to have a 5x on the end of them. Okay, and we do not have that here. This is not in S. I don't need a lot of fanfare. I don't need a lot of not really a check mark here. I don't need a whole long big essay about this. This is kind of just glance at it, and it's clearly not in the right form. And so this fails. The zero vector check fails. So do I have to go on and look at any of the other axioms? Nope, this is game over. This is game over. If something fails, then right away, then the answer is no, this is not a subspace. By the way, just to humor us for a second, let's say we did decide to just play dumb and just say, oh, let's just check the closure under addition. Okay. If we did that, if we said, okay, we'll take AX cubed plus 5X, and then we'll take, what was my other letter, RX cubed plus 5X, that would be two vectors in S, and I add them together. You can see pretty quickly what goes wrong here, right? The A plus R is fine, but what are you going to be adding on the end of it? 10x. 10x. Well, that's not the right multiple of x anymore. the 5x and the 5x turned into 10x, well, that's wrong. We would again end up saying that this is not a subspace of V. It's not closed under addition either. And the scalar multiplication is also gonna fail. Everything is gonna fail. Right. Okay, let's do one more and then I'm gonna let you guys practice a few, okay? Unless there's any questions so far. Are we doing okay? Yeah, please.
Checking the zero vector for polynomial, we're substituting the coefficients, not variable.
You're absolutely right. I'm glad you brought that up. Because that is something I do see from time to time with polynomials. When people want to check the zero vector, I'll see them putting 0 in for x everywhere. And the x is actually just the part of the vector itself. That what changes from one vector to another are the a and the c. The x cubed and the x, those are sort of fixed pillars of your polynomial that you're not really allowed to tweak. You're not allowed to do anything with them. They just have to stay there.
I have a question.
Please.
The last one we just did, the ax cubed plus 5x.
Uh-huh.
Checking the zero vector.
Yeah.
Where did you plug in 0 for the 5x part?
I didn't, I couldn't do that, right? What I did instead is I said, well, what would my zero vector be looking like? And it would have zeros in all of its coefficients. And that 0 not being a 5 really means it doesn't have the right form to be in S'ing.
Okay.
Yeah, that's a great point. It's a great point. Okay, let's do one more here. So let's do number 3. Let's take V to be the n by n matrices this time. So I'm going to use a different universe here. And S is going to be the set of capital A, which is an element of V. By the way, you notice that I'm trying to use notations that are nicely fitting in with the universe we're talking about. Sometimes I'll see people like over here on this one, which has polynomials, I'll see people use A and B over here. Technically, that's not wrong. You can use whatever letter you want for your sort of hypothetical verification of the closure of addition here. But using A's and B's for polynomials, that's not really the context I think of for A and B. I usually think of those as being matrices. So over here, same thing. I would not use P of X over here because we're not talking about polynomials. So what do we usually write matrices with? That's usually capital A, capital B, something like that. Right. Okay, and then here's the condition: determinant of A equals 0. So we'll tie this back into the last chapter now, and I want to know whether S is a subspace of V. Okay, and so for the solution, let's get right into it here. Let's check the zero vector. Remember, guys, the zero vector check is kind of like a gamble. If the zero vector check passes, then you basically wasted your time doing the zero vector check. But if it fails, like it did on number 2 just a moment ago, you get a fast no. And it's immediately not a vector space, and it's nice to then not have to do anything else. Right. Sometimes on my second midterm, the very first problem, just to get everybody warmed up, I'll ask them, here's something, is it a subspace? And there won't even be a zero vector. They just say no, and then you've already got the exam partly done in like less than a minute. So it can be something like that, right? This can be very good when it fails. Let's see if it fails here. Let's see. If I take the zero vector, in this case, the zero vector would be the zero matrix. So it would be the matrix of all zeros, which I can write as 0 sub n. What is the determinant of the matrix of all zeros? Yeah, it's just 0, isn't it? It's got to be 0. And so that actually implies that that zero matrix does meet the requirement for S. Let's put a check on that. It does actually pass that. Okay, so in other words, we just wasted our time. It's basically what it says. Okay, but that's okay. Does that mean it's a subspace? Not yet, not yet. Just because it passes the zero vector check Well, we still have to go through the motions. You saw an example in my video where the zero vector, I think it was the parabola. There was a parabola in the video and it did have 0, 0 on the parabola, but it was not a subspace. Right? So let's just not get too excited yet. We've got to check the addition here and the scalar multiplication. So for closure under addition, we could say let A and B be elements of S. Let's say we take two vectors that are in S. Now, what does this mean? Then this means determinant of A is equal to 0 and determinant of B is equal to 0. So we would have both of those things. A and B both have a determinant equal to 0. All right. What we're really up against is whether or not A plus B would have a determinant of 0. So would that be true? If the determinant of A is 0 and the determinant of B is 0, would the determinant of A plus B be equal to 0? Edgar? Yeah, my sort of nagging sense in the back of my spine is that didn't Dr. Annan talk about how the determinants don't play nice with addition? There is no formula for this. I can't just split this apart. That's making me feel really uneasy about this, right? It's making me think maybe this isn't going to work, right? And I probably should put this on pause and see if I really want to press this forward. It may not work. One of the things that's challenging about this section, guys, is that you sort of need to have a gut feeling ahead of time. Because the way you're going to proceed when the closure under addition or scalar multiplication does work is what we're doing so far here, which is you take two arbitrary letters, you set out what it means, you're doing everything in the abstract, right? But then if the axiom actually fails, then we have to do something completely different, right? When an axiom fails, what was it again? All Saturdays are sunny, that fails. We just need one example, a specific example to show that the statement fails. And I think we can make an example here. Even though, so I'm going to completely cross this off. What I'm trying to show you though, by messing this up, is that that's normal. And you might do a homework problem for next week and you start off trying to show that it works and then somehow you hit a wall. You're like, that just doesn't seem to work the way I thought it did. Maybe I should rethink this a little bit, right? And I think we can make an example, and I believe that this is going to fail, mainly because the determinants do not play nice with addition. Would you guys agree that the matrix 1, 0, 0, 0 is in S? That's in S, the determinant is 0, right? And would you also agree that the matrix 0, 0, 0, 1 is in S? So you can think of this as A and this is B. Now let's look at A plus B. A plus B, we add them together slot by slot, we get 1, 0 and 0, 1. Is that in S? No, the determinant is not 0 anymore. That is not in S. And this shows that the closure under addition actually fails. It actually fails in this case. And so it's game over. It's game over. This is not going to be a subspace. This one is not going to be a subspace. Okay? Clear enough? But yeah, sometimes you don't know and you start trying to prove it's true and then you realize, oh wait, that's not going to work. So, and then you just try to give real simple examples. Do you guys remember the question on the test about rank? I had rank of A plus B and I said, is that equal to rank of A plus rank of B? Well, it's definitely not. But I had some people writing out 4x4 matrices and with lots of messy numbers in them. I'm like, wait a minute, just use like 2x2s. Actually, this would show that right, the rank of A is 1, the rank of B is 1 and oh, this doesn't work. 2 does equal 1 plus 1. Sorry, I would have to change, I'd maybe make this into a minus 1. There you go. So now you've got 1 plus 1 equals 1, something like that. Anyway, sorry. Don't change your notes for that. I'm gonna go back with this the way it was before. Does somebody have a hand up out there? Yeah, Edgar?
What would be the notation for the determinant of that last matrix?
For this one?
Yeah.
The determinant is just 1 times 1 minus 0 times 0.
No, I know, but what would be like, how would you write it down, like determinant of A plus B?
I notice I didn't write determinant in front of any of these matrices. All I did is just in my head, I did the determinant and then I said yes or no, is it going to belong to S? This is all you need to write down. You don't actually need to say anything more than that. These symbols here address the issue of membership in S, so you don't need anything else besides that. Yeah. Okay, we all good on that? Okay, great. Well, guys, I would like to practice a little bit more and have you guys try a few of these, okay? And see, you guys are a little bit tired. Were you watching my movie at like 2 in the morning or something? I know I felt bad to give you that work right after the exam and everything, but I really appreciate y'all doing it because it does help for sure with getting through this stuff. This will help get you awake a little bit. I'm gonna give you about 15 or 20 minutes to just go through the group work number 6 here with some buddies. You can use the whiteboards, but here's the thing, on the sideboard, you guys all see over there on that left word where it says GW number 6. What those are is those are hints for each of these problems. So what you'll notice, for example, part A is actually the one that I just did right here. So you don't have to do part A. Part B, the hint is, I think it says skew symmetric matrices. I said, see your notes from the video because in the video I did the symmetric matrices. So you can do that. Part C, I'm going to suggest to draw a picture of the set. Part D, I want you to think about null space. So I'm giving you a few ideas on how to help yourself out with that. So let's take 15, 20 minutes. Go ahead and grab 2 or 3 people. I would love to get you up at these boards though. So I'll erase and give you guys some skill. Thank you. Okay, guys, let's stand up. Stefan, up. Daniel, up. Please. Everybody should be able to find some space.
You like all this.
Take turns with the markers. If you don't know everybody in your group, just start by introducing yourself a little bit. You can start by introducing yourself a little bit. Come on down. You guys aren't going to make any mistakes, right? So then I can have you on the YouTube camera for the whole world to see. So no pressure here.
Just one at the.
Yeah. Also, if you need help.
Anybody need help?
Oh.
Yeah.
Problem is. There has to be three that go on the same thing.
Oh.
Yeah.
Oh.
But that's an, yeah, it's a better idea than actually remember. This is gonna be their lady. This is where it's like. If you use it. Video. It's like, it's a conflict. So that was the.
I'm at the next one.
It's really good starting.
Excellent.
I see the picture that you guys have there. Ooh. No, it is actually not quite right. If you think about this, guys. This is both sides. The same come up with the X and the Y are just pluses and minuses. So it actually should be zero. It's like this line, which is the line right left, and this line. Like negative. And both lines put together. The question would be, this is the picture you want to think about. It definitely has the zero vector. The zero vector is right there, that's on the X, right? The question is, what would be big X, the big black X, would that be closed under addition? Or would it be closed under? What you think about it, talk about it with yourselves, and then I'll come back and tell how you're doing. Looks good. I would probably, before you go to this, I would probably start by taking this and saying, all right, this means that A trans. So E becomes one and one negative. I like the. Yeah. What does it mean for A and B individually? For them, it's like, oh, I see. Yeah, you replace the negative rates. Stuff to do. Do you know what to do next? One more thing. One more thing.
No, so I.
So is A plus B satisfying the main condition over here?
Transpose of A plus B negative.
So this implies, let's not just also be sure we write down the which is A plus B is so that's the. Good job so far, guys. That's the key equation. A transpose B. Go. Do that.
Well,
And go to SI,
I did see that.
which would be right now.
Wouldn't- On the video, I was doing symmetric matrices, so we're going to do transpose.
Yeah.
The same idea, the only difference here is we have that minus. So the question is really gonna be, does the minus sign mean? So I seriously try to avoid getting our hands messy.
I would do one
Be a whole lot.
plus negative 2. Yeah, do 1.
So we don't have a number.
Plus negative 2.
Can I see what you have? That's a matrix of all zeros. Yeah, that is the zero matrix. Now, is it in S? You transpose that matrix.
Yeah.
Would it be the same thing as if you took the negative of that? You're gonna get all zeros, right? So it passes. It passes. Closure under addition. That's right. In my head, I think the all zero matrix, we really need to do it. Yeah. Transpose, it's just it's yeah, and the negative is just themselves. Not too interesting. So I'm gonna give you the first sentence. Well, actually, if you need to, he's got the first sentence, because he's got the notes where I did the symmetric one. And you just wanna basically take those notes and go through it with this example and say, can I go the same way as the notes all the way through? I will let you work on it. Anybody need a hand?
Yeah, one. It's like you pick any point on square. So the 0 factor is.
Sorry. So back to this.
So if you pick any random.
Yeah.
So I think that's like. It's just like. Which is the
Why?
it's you add those any points on here that we set. It's another way to turn it on. It is out of order. That means- It does.
Yeah, we're gonna be asking, so, okay, if I like this, I'm not. Parabola.
Yeah.
Yeah, you add those together, you get. Go ahead. It would have to be on either one of those.
But
Yeah. So say if you add, zero and.
you can say yes.
One. Yeah. You get one. So then it is an element of that.
So you're not gonna do singing.
It would. It gets strict. It's just like. Yeah. And then you get really.
And like for this one, here, we can enjoy. Don't ride it.
No, everybody's got their own.
So then,
No,
No,
This would be like, go out on Saturday.
thank you so
We're
much.
gonna try cards and.
So I don't know.
Well, usually.
Well, they did the same thing. They did 1-1 and then 1-1.
Oh, okay.
Oh, we did.
Yeah, it's okay. It's still a.
So when did you say?
It's got an.
Oh.
No way.
Yeah.
That's the high as a heart.
Yeah, that's 7. I expected to be Where was I?
I'm gonna show you the easier way to do that.
Yeah.
That's why I said to skip it for now, but.
Yeah.
I agree.
Like you said, well.
That's the order. Same one is here. Negative one is here. So I can say, you got a hand, that's not not an S.
Yeah, we are. Okay, so we made it like, so.
For the X one, under addition, so have 2 points both on the big X, which you add them together, it's not. So this one fails, game over. Same thing. So you guys are working here with general letters. But you see what these guys did is they made a specific example. Because when something fails, I don't have to do it for like it's big and random letters. I can actually watch specific numbers and show.
Yeah, I don't know if it's so far, but I'm gonna go through how to.
Try to draw the picture in the XY plane, but they were consistent 2 lines.
Yeah, I had electric.
Hey guys.
Like I.
I think I said in my video. But I did say it's top points. If. First line right here is.
Two to
what we
five
should
was
add
more
or
meaningful.
say
Yeah.
not just
I'd
confirm.
rather.
Oh, yes, that is, yes, that's what it's showing. Is that there are two things in this.
Yeah, and it's on here. This is.
Checking me on my notes. Did I good? Did I write A plus T to element of S? I'll write better. I guess. Because otherwise I'd be taking off points on this. I think here, I would put the minus. Thing here. Here it's
You guys think.
factor it out. And now you have,
You don't have to think.
Yeah.
okay, A transpose equals.
thing that I don't
okay,
like.
Yes, that's right. Yeah, actually, this should.
Now there's.
Let me show you. It's fun. As opposed to this looks like two things. It is true. Actually, this is just.
About you, what are you?
Not.
Here.
This is the vector.
Oh, yeah, so we have a lot of the same concepts.
Right, A times A.
But like,
See?
but
yeah, so this.
I don't think doubly through.
It looks like.
Copy doesn't do map file.
Here to here, here to here.
Oh, yeah, there's no like power lab, there's no electronic mechanics.
Why don't we do?
More like two more coding classes. Yeah.
But everybody will tell you what to write, so you don't even have to stress out.
Taking the classes.
Yeah, right.
Yeah, I'm taking the last one, 131. I'm taking 120 right now. I don't like it.
So,
Really? I don't like it.
this could be.
I don't know, it's just,
It's not.
like with other stuff,
Maybe another.
the process of it,
However,
at least in my opinion, is rewarding, you like it. But
is those from.
coding, I just don't like the process. Yeah.
Yeah.
120 and 120.
Yeah.
Yeah.
Let's say.
Yeah.
Yeah.
And I tried to learn Python before. I mean, it's kind of similar stuff, like the commenting, is like hashtag. So like the pound. I haven't done Python. Yeah, if you're gonna need like. I took that last. So we're on the second. So we're on. So.
This would be.
So first let's go through.
Junior.
Reagan took like these that I need to get like we have these.
Yeah, I should.
Thank you. I'm so sorry to interrupt. I'll bring it right back.
When I heard your voice, I was like, that sounds like Warren. As far as I know, he's not taking this class.
48.
Right.
I'll bring it right back. Okay, no, you said right. I'll check with it.
Thank you. Thank you. Yeah.
All right.
It sounds like, might as well like get caught.
But your keys are back.
Thank you, Lori.
Thank you very much. I appreciate it.
Zero. You get one. Points that both those drafts that both those zero ones and then add them.
Yeah.
You're gonna end
Yeah, like, go home, I don't do it. I have to stay here.
Hey, guys, I'm gonna go ahead. You guys are all doing a great job, and I know I gave you a whole bunch of parts to think about here. I'd like to go ahead though and give you a little bit of a break, because we've been going for a long time. If you want to take a few minutes and go outside, get some fresh air or use the restroom or anything, that would be great. We'll have about 15-20 minutes at the end, and I'm gonna start talking about something a little bit new when we come back. So feel free to bring this to a close and get some fresh air and take a break if you need to. Did somebody have a question for me though? You guys, did you figure this out? You got the picture right. So here's a point that's one. Here's a point that's
One or two.
I add this together and end up here.
Yeah.
I had a photo in the video, but it was exactly.
So.
Yeah, I'm taking.
So it's not giving us like, you have to go to the.
Yeah. And then coding class, and then that button, so that's it. And I was gonna try to do one more class, but I couldn't get into it. Do you want us to erase?
If you are good with what you've got up there, if you want to take a picture of it for screening anything from it, otherwise you can erase it, that's totally fine.
CHDL, which is 2 more units, so 6 units of car. Basically, programming FPGAs.
Okay.
Field programming. I don't know what I forgot what they used for, but they're important. So yeah, this class, HDL, 131 and 401. I wanted to take
But it's not bad.
the LSI class. I wanted to take 456, but it wasn't available. It's like it said it's going to be available like this semester, spring.
Which class is that?
It's I think it's intro to VLSI design or something. But I couldn't find it.
Yeah.
I checked out.
Yeah.
Yes.
So we'll maybe offer them like during spring, right?
I was road roll watching that.
Yeah, no, that's great. Actually watching this.
Yeah, that's what they do. Sometimes it's only like 1 or 2.
Well, he likes this the ones, but it's
Which, you know.
Yeah, exactly. You probably wait another year.
We graduated 4 years in your futures.
Yeah.
No, take summer classes.
Summer classes.
I don't think I
That was
was.
the first one.
Yeah,
I
thought it was like a summer class for this.
Well, they don't want to go.
I would.
Well, I was like, yes, pretty fun. Yeah, I like, I can't go, I go, I was thinking, was one thing, let's get out. Yeah. And so they put it outside.
Yeah, it was crazy. I mean, it was rough.
It's like one exam a week, right?
Yeah.
Still doing the same one?
We're on C.
Oh, yes.
Oh, you're on C, and you see the big X is the picture, right?
Yeah, so this is.
Yeah, I agree, because then.
But
The zero vector definitely passes, right? Yeah, we got that.
Yeah.
And now you're working on the addition. And now I.
Do you think it's going to be closed under addition, or do you think it's going to be not closed under addition?
I thought it was similar to the one that you did like with the parabola. And if you remember the parabola, I gave an example. I gave specific points.
As long as I don't have to go to like.
It was like.
Exactly right.
Yeah, that's like my-
Exactly right. You know what? Those exact same points for the X to.
Oh, yeah.
You could literally take exactly the same
But you have to
point
sell your soul.
and you're gonna show that it's not closed under addition with that example.
I like that you weren't.
Yeah, that's really good. That's really good.
I don't know.
Yeah, I like what's the best.
Yeah, take that.
What's the next one about the other ones? Just Yeah. That's okay. Wait,
That's what
One time, but
eighties and nineties.
a nice example of that would be.
like, there's like a tiny rover.
Oh, okay.
Formula.
Ask
you 0, 1.
Yeah, oh yeah.
It's like.
My daughter.
Add those questions together.
Yeah.
Yeah, they're going to use the prayer. But they, I haven't. My son, but it's. But that's like we're like. Not one, but now it's like. Because it's already knows that I just.
Yeah.
So it's really hard.
Yeah.
I can have video.
Yeah. Does she just speak? English? Yeah, I'm saying English.
That's Spanish, English. I mean, my son was more more English now. Yeah, I wasn't, I never thought I would. That's not, but.
I wanted to move to Canada like first.
We tried it, it's not like.
When I but
She
she's
likes
too
the.
far. I was actually gonna do comp sci.
Something like
But I
wanna get the other. I wanna do it more like 2 years.
Well, they look,
Yeah, she can.
I looked into it.
It's
and
hard, it's really hard.
I kind of realized.
So hard.
Hey, Candace really wants to do it.
So my niece, my niece,
And it's.
yeah.
I was like, it doesn't really demand the stuff that I was looking for. Like,
Okay. My wife is.
V8, so
Cambodia, Vietnam.
big red diesels.
Laos, you know.
Yeah. Yeah, my niece.
That was gonna do electric, but then I had this one guy who he graduated a couple years ago.
And it was like,
He insisted that I don't do that thing because apparently I was pretty bad.
Trouble keeping this thing standing up. There we go.
I have a question.
Yeah.
For like a matrix, like, can we like do row reduce echelon form? And if a special solution exists, like, wouldn't, no?
No. That problem is not really not doing here.
No, but like another problem, similar, like if we're given a matrix.
No, EROs and closure under addition are kind of closure under scale multiplication are have not related to each other.
But then can't you like find the null space during EROs?
Well, if that's what you're interested in, but your subspace There's lots of examples about matrices. in this.
I have to shift.
Guys, I think, I might try to get us back together here. Just a quick reminder, guys, that, because I know not everybody got through all of the group work, because there were several parts to it tonight. But just a quick reminder that the solutions to all of these group works, they are in Canvas. So if you didn't finish and you need a little extra practice, you can certainly read my solutions there. I didn't see too many groups get to part D, so I just decided I'll just throw this up on the board and see what you think about it, because this one's pretty quick.
Yeah.
Let's just talk about part D real quick. Suppose that S is the set of points in R3, X, Y, Z. Those would be 3 slots in R3, such that 2x minus y plus z is equal to 0, and negative 4x plus 2y plus z is equal to 0. And I want to know if that's a subspace or not. So is that a subspace of R3 or not? And I'm wondering if anybody has any idea about that, except for the back row back there. I mean,
Well, this is more just a question than an answer, but
okay.
is a subspace only 2D or can it be 3D?
Oh, subspace can be anything. It could be, and we aren't even talking about dimensions yet. So 2 dimensions, 3 dimensions. We are going to have a concept of dimensions fairly soon. But at this point, remember, most of the time, the vector spaces we look at, you cannot visualize what you're looking at. If it's polynomials, we don't have pictures. If it's matrices, we don't have pictures. So we're not going to be able to rely too much on our visual sense of things. I could very easily crank this up to R4, R5, R6, make a new example. Okay, but I really want to get to the crux of it is these equations here. So what do you guys think? Does anybody have
Put it in
an
the
opinion
matrix.
about it? Pardon?
I say put it in a matrix.
Put it into a matrix. And what were you gonna say?
Yes, because you can write it as a null space.
Yes, because you took the words right out of my mouth. Yes, because you can write it as a null space. It even says it on part D over there. Think of it as a null space. This is a null space, right? So you guys watched my video, so some of you already probably remember it from that. You can express it as a null space, and you want to show me how, right? What I mean by that is you should write down the matrix. So you just grab these coefficients. And by the way, with this matrix, you don't have to put the augmented far right column. You just put the coefficient matrix here. And anything that is expressed as a null space is always a subspace. So the answer is yes, this is a subspace. Okay, just because it's a null space. So if you're going to use that justification, because I think it does come up on some of the homework problems, the main thing I'm going to be looking for, or that I'm going to ask my grader to look for, is did they write down what the matrix is? So you just have to write the matrix. You don't have to do any EROs. You don't have to actually solve this system. That's not the point here. We're not trying to solve the system. We're just trying to see, is it actually a subspace? And in this case, it is. What would happen if let's just make one more. I'm going to call it D prime, which wasn't actually on the handout. What if S was the set of X, Y, Z in R3 such that 2x minus y plus z is equal to 0 and negative 4x plus 2y plus z is equal to 1.
Ooh.
If I just change that very last number, surely some little tiny tweak like that won't mess it up, will it?
It does. What was it?
Is that going to be a subspace?
No.
I don't think so. I don't think so. Not a subspace. And what is the reason? I think I heard it. The zero vector check. Exactly. What is my zero vector of R3? It would be 0, 0, 0, right? That is the zero vector in this universe. And does it work? Is it a solution to the equations? It doesn't work, does it, in this equation over here? If even one of the equations fails,
then that vector is not in the set. And so this thing fails the zero vector check. So guys, if I give you a system of equations, right? You're either gonna get a fast yes because it's a null space, or you're gonna get a fast no because it fails the zero vector check. On these kinds of problems where it's a system of equations, you should never be forced into actually checking closure under addition and scalar multiplication. You should never have to get your hands into that amount of detail because you're either gonna have a null space or a failure of the zero vector check. One way, it's gonna be one way or the other, and it just depends on whether there's an equation whose right-hand side is not zero. Yeah, Edgar?
So the shortcut method for that would be to see if all the equations equal zero.
Pretty much. Pretty much, yeah, exactly right. So there, I think I have some homework where I have 2 or 3 of those in a row, and yeah, it's all you have to do. Kind of look at the right-hand side of those vectors, of those equations, and see if they're all zero. Yeah. Any other questions about any of that? All right, well, yeah, over the weekend, keep practicing. There's some homework for you for Tuesday to work on this closure under addition idea, closure under scalar multiplication. The write-ups of these verifications is really what you need to spend some energy focusing on. When something fails, you're going to be giving a counterexample to it. And that's really going to take just a little bit of practice, I think, and we should be good. I'm going to take just a few minutes to give you a quick preview of this next section, though, and give you some ideas of where we're going to go next week. And this is actually kind of starting into the next section already. Just take 10 minutes. It's not going to take long. This is a section that is called spanning sets. Spanning sets. This is what I want to wrap up tonight talking about a little bit. And the idea here, let's try to write down an idea here for you. The idea is to start with a handful of vectors. I'm going to label them here as V1, V2, and ... up to Vn. Remember, I'm always trying to put arrows on top of my vectors so we can recognize them as vectors. Start with a handful of vectors in your vector space V. So you already have a vector space in your hands. And I want to grab, I'm just going to, dig in, close my eyes, dig in and grab out a bunch of the vectors, right? These could be a bunch of matrices. It could be a handful of polynomials. It could be a handful of calculus functions, whatever they are. I'm going to grab a handful of those vectors and try to make them into a subspace. I would like to have a subspace out of that. If I just grab into this, if I blindly grab some vectors out of this vector space, are they probably going to form a subspace right off the bat? Well, if I did, first of all, if I did not happen to grab the zero vector, then it would not be a subspace, because we know that the zero vector is required. And even if I did grab the zero vector, if it's not closed under addition, it's not going to be a subspace. Let's say I grabbed the vector 1, 1, 1, and I grabbed the vector 2, 2, 2. Well, then I better also have grabbed 3, 3, 3, and 4, 4, 4, and 5, right? If I didn't grab, if I missed one of those, I'm out of luck, right? Chances are not very good that your handful of vectors is already closed under addition and scalar multiplication. The idea on this section is that we are going to take this handful of vectors in V and we are going to close it up. I'll put that in quotes. Close it up under addition and scalar multiplication. We are going to close it up under addition and scalar multiplication to create a subspace. It won't be a subspace until it is actually closed under the two operations. That was what we learned about subspaces. They have to be closed under addition and closed under scalar multiplication. So we're going to create a subspace by just grabbing these vectors and closing it up under addition and scalar multiplication. I'm going to show you what that looks like in a second. This subspace, when we create a subspace this way, what we're doing is we're creating a subspace that is spanned by that handful of vectors v1 and v2 and so on up to vn that we started with. We're going to create a subspace that is spanned by those vectors. Okay, now the question is, well, what do you mean close it up under the operations? Well, if I grabbed 111 and 222 out of the R3 vector space, then I'm going to throw in 333 and 444. I'm going to go back. I'm going to say, okay, it's not closed yet. Let's throw in some more vectors. Let's close it up by throwing in additional vectors that will make it so that it's now closed. It's not closed yet. Originally, the original vectors are probably not closed. But if I throw in enough additional things, I could make it be closed. You know, if you want a really simple example, something where we can even just draw a picture of it, just imagine, let's just take the universe of R2. That's my vector space. And let's say that we just have just one vector that we grabbed. Let's say we grabbed the vector 2, 1. So that's V1. Is the vector 2, 1 by itself a subspace? Just that one dot? I don't think so. I mean, as I just mentioned, by itself, 2, 1 is not going to have the zero vector. We would need to have the zero vector in our set as well, right? And we would have to have 2, 1 plus 2, 1, which would be 4, 2. And 6, 3. And also scalar multiples of 2, 1, like 1 and 1/2. And negative 2, 1. The scalars could be negative also. Negative 4, 2. What am I getting as I'm filling in dots here? All scalar multiples of the 0.2, and what am I forming out of that? If I were to keep going and keep taking that, it's not a subspace yet. This little smattering of dots is not gonna be closed. But if I throw in that dot, and then I throw in that dot and that dot, what am I ending up with here at the end of this process?
Right.
The name of this class, right? Linear algebra. There's the word right there, my friends. Right? There is a line in it, right? This is it. This right here would be S. That would be S. That's my subspace now. So just the vector 2, 1 is not a subspace. But if I close it up under addition and scalar multiplication, I'll end up with this entire line. And I'm going to express this S as what we're going to call a span. I said that it's a subspace spanned by. So let's just write it like this, guys. It's the span of 2 and 1. It's the span of that vector 2, 1. In other words, we're taking 2, 1 and we're closing it up under addition and scalar multiplication. And this is a subspace now, the whole line. If you take 2 points on this line and you add them together, you will stay on that line. And if you take 1 point on that line and you multiply it by a scalar, you'll stay on that line. So it's definitely going to be a subspace now that we've closed it up. So let me write down a couple of very quick definitions, and then we will pass back your exams and get out of here. Okay, so really quick definition. And then we'll come back to this obviously next week as well. So given, here's a definition for your notes. Given V1 and V2 and dot, 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 up to Vn, a so-called linear combination. Here is another popular word in the world of linear algebra. A linear combination has the form. I'm gonna write down the form of a linear combination for you here, guys. It is basically anything that you can build out of these vectors by using the vector space operations, addition and scalar multiplication. How's that gonna look on paper? Well, it's gonna be a constant, I'll call it C1 times V1 plus C2 times V2 and plus dot, 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 plus Cn times Vn. Anything that looks like this is a linear combination. Now, in the example that I did over there, I only had one vector, which was V1. If I only had one vector here, I didn't have n of them, I only had one of them. You can see what you would have had would have just been this part. And what is this? This is just scalar multiples of your vector. There would be no other vectors to add because you're just getting rid of all of that. Well, if I take multiples of the vector 2, 1, that's gonna give me the entire line, isn't it? It's exactly what it is. Okay, and then one last definition, then I am going to call it good. If we take all of these, so the set of all possible linear combinations the set of all possible linear combinations of V1, V2, and dot, 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 up to Vn. If we take every possible way of putting scalars in front of my vectors and building an expression, right? This is called the span of that list of vectors. So I use a braces here around V1 through Vn. The span of V1 through Vn. And by the time you take the span of a set of vectors, my friends, by the time you do that, by the time you take all possible ways of starting with your handful of vectors and doing vector space operations on them to build these linear combinations, if you are diligent and you are patient and you write them all down and you make this span, you will have a subspace. This is a subspace, and this is the theorem that I will wrap up with, and we'll do tons of examples of this next Tuesday. Anytime you take the span of a set of vectors, you are basically saying you've closed it up under addition and scalar multiplication. The span is always a subspace of V. I'm just giving you the cheapest way in the world to make subspaces. Every one of us in this room can pick our favorite vector space, grab a handful of vectors, such as what I did right here, and form the span of whatever those vectors are, and we will be guaranteed that it will be a subspace. So guys, there are not just sort of one or two subspaces out there. They are everywhere. They are everywhere. You grab whatever vectors you want, you form their span, you've got a subspace. We'll talk more about that next time. I'm going to give you back your exams, and then once you get your test, you can go. We're just about out of time here, but I would like to get these off of my hands and let you go from there. Omar, I don't see David here right now. Is Daniel Perez here? We go, Elijah, Edgar, Glenn, Kevin, Vega, Steven, Johanna. Nancy, live.
Joe? Andy? Joe? Anthony? Vaughn? And Anthony? James?
Turn this off.